We now consider a couple of sample problems from the end of section 5.3. The first one is problem 576, where we have an I-beam that's in a statically indeterminate configuration. So in figure A, it is built in or clamped at A on the left-hand side, and it's roller supported at C. There will be a total of 3 reaction components at A and 1 at C, so it's statically indeterminate. But under certain circumstances, the problem statement says it may be appropriate to use the model shown in figure B, where the I-beam is rigid. And that's going to be an important qualification in this problem because it's going to tell us something about how the beam is going to deform under load. So here, the built-in support at A is going to be replaced by a pin and torsional spring with stiffness K sub T, and the roller support at point C is going to be replaced by a vertical spring with stiffness K. We want to use this model on the right to determine the reactions at points A and C, expressing the answer in terms of parameters such as the force, the length, and the spring constants. Take a few minutes now to try this problem yourself. Resume playing when you're ready to see a solution. So as I mentioned, the key phrase in this problem is that we're treating the I-beam as rigid, and that may or may not be a valid assumption, but if we are treating it as rigid, that tells us something about how it's going to deflect in the model at B. Under this force, it's going to experience a vertical deflection at C, but if it's rigid, it's going to be experiencing a rigid body rotation about A, and the deflected shape will just be a straight line. That's important because it's going to tell us something about the relationship between the vertical deflection experienced here at C and the angular displacement of the body at A. In particular, theta is going to be equal to the deflection at C divided by the length of the beam. If we consider our free body diagram, we have a pin connection at A, so we have AX and AY components. And the force exerted at B is tending to make the body rotate in a clockwise fashion, so the restoring moment from the torsional spring will be in the opposite or counterclockwise direction, and that restoring moment will be equal to the torsional spring constant times theta, which we can see is the deflection at C divided by L. We also have the force acting in the middle of the beam, and then we have a restoring force at C, which is going to be equal to K times the deflection at C. Because we have this relationship between theta and delta C, we can solve for delta C directly by taking the sum of the moments about A and setting that equal to 0. We have a counterclockwise or positive contribution from C through the length L, so that's going to look like K delta C times L. We have a clockwise or negative contribution from F, that's acting through a moment arm of L over 2. And then we have the restoring counterclockwise moment from the torsional spring constant, so that's plus the torsional spring constant times theta, which is delta C over L, equals 0. So if we rearrange this for delta C, we have K times L plus torsional spring constant over L times delta C is equal to, on the right-hand side, F times L over 2. And then if we multiply both sides by L and rearrange this, we end up with the deflection at C is equal to FL squared over 2 times KL squared plus the torsional spring constant. This in turn gives us that the reaction at C, which is K delta C, is half of the force times this ratio of KL squared to KL squared plus the torsional spring constant. One of the checks we can use on this problem is to ask, what happens if the torsional spring constant goes to 0? If the torsional spring constant goes to 0 in this model, then A just turns into a pin support, and it would be a statically determinate problem where we would find that we would have equal force distribution between the vertical support reaction at A and the pin at C. And so this result for the reaction at C tells us, in fact, that if the torsional spring constant goes to 0, then that second term becomes 1, and the reaction force at C is just half the force F. So in the limit that the torsional spring constant goes away, we get a result that's consistent with a simple statically determinate problem. We can then use force equilibrium to get the remaining components. The equation in X is trivial. We're just going to get that AX is equal to 0. And in Y, we're going to end up with AY plus C minus F equals 0. So having C now, we can rearrange this for AY and show that AY is equal to F over 2 times KL squared plus 2 KT over KL squared plus KT. For our second problem, we have problem 577, which is a qualitative problem. We have a square plate, and we want to specify under the conditions shown whether it has partial or full fixity and whether it is statically determinate or statically indeterminate. The problem statement actually refers to two problems, 577 and 578. There are cables in 578, and so the comment about assuming that cables are in tension is not really relevant for this particular problem. But it also says that we're to assume that the rollers are in compression, which suggests or implies that in this problem we're to take these rollers as literal rollers that are unable to pull the object towards the rollers. Nevertheless, we'll proceed by looking at each of these cases, and what we'll do is we will make a note of all the reaction components that are existing in each problem and try to look to see if there's a configuration of supports that will result in partial fixity in some instances. Take a few moments now to try this problem yourself and resume playing when you're ready to see a solution. Let's note that in all 6 of these cases, we have a pin support at the upper left, and so we're going to have 2 reaction components there in all 6 cases, and I'll just begin by making a note of that. What that tells us in all 6 cases is that the body will not be able to experience a rigid body translation because it's pinned in the upper left-hand corner. It could potentially undergo a rigid body rotation about that pin, and we'll want to investigate that as we go through these individual cases. Now at A, we have a roller support here at lower right, so we're going to have n equals 3, and this configuration will prevent a rigid body rotation. So this is going to have full fixity, and if we did have some kind of an external force applied, this would be statically determinate. At B, we've got a roller support in a different location, and now this is going to be a somewhat unusual case because, again, we're going to have a situation where the lines of action of all the reaction components go through the same location. They go through the pin. Now we could divide this up a little bit further. If we had a situation where we had an external force that had a line of action that went through that pin as well, suppose we had an external force that looked like this, then we have a 3-force member where the pin at A is a point of concurrency, and that's automatically in moment equilibrium. But if the external force didn't do that, if it was over here somewhere, we would have rigid body rotation about that pin. Now, as soon as we started to do that, what would happen is that as we tried to make the body undergo that rotation, more of it would be tried to be squeezed into the space between those 2 supports, and we would get an increasingly large normal force there at the roller that would cause some binding. So we might have eventually a friction force that develops that would act to oppose that rigid body rotation. This is like one of these problems that has the ability to undergo a rigid body rotation, but under a very limited range of motion before some change in the geometry would result in a restoring force that would bring it back into balance. Nevertheless, this configuration with the roller directly underneath the pin would be one that would enable rigid body rotation about the pin. So this is a problem involving partial fixity, and it would be statically indeterminate. In case C, we've got two roller supports at the bottom. We have n equals 4. This will have full fixity, but it will be statically indeterminate. In cases D, E, and F, we have short links on the bottom right, and these are pin-supported members with no intermediate forces. So these are going to be two force members, and the line of action of the force that's transmitted by that member will go between the pins. So in case D, the support reaction is like this, and in E, it's like this. And in both of those cases, we have n equals 3, and we have a statically determinate problem with full fixity. So both of these are full and statically determinate. For case F, we have a situation where the line of action of this short link is going to go again right through this pin support. And so we again have a situation where if we have take moments about that pin, we're going to get 0 equals 0, and we've got the ability to undergo a rigid body rotation about the pin. So this is case F is going to actually look similar to case B in that as soon as we start to experience a rigid body rotation here, the geometry of this link is going to change, and then it will develop a restoring force whose line of action no longer goes through that pin. So just as in case B, we have a situation where we have the ability to undergo rigid body rotation about the pin, but it's going to be a limited range of motion before finite deflection changes the nature of the problem and brings it back into balance. So this will also be one of partial fixity and statically indeterminate.